In this lecture, what we're going to look at is a concept that's hidden neatly in all of the problems that we've tackled so far concerning the dynamics of objects. In particular, this concept is known as the conservation of energy. Okay, basically, conservation of energy says that energy cannot be created or destroyed. You may have heard this before. But transformed or transferred. Or transformed into other types of energy. So this is the wordy sort of meaning behind the conservation of energy. Now what is energy? Well, you may have heard of this in school. And there are many forms of this. Well, you may have heard about things such as kinetic energy, types of energy. You may have heard of kinetic energy. And this is the energy an object has due to its speed and mass. Okay, so if an object's going at some speed, it has a kinetic energy associated with this that allows it to go at this speed. Potential energy, this is the energy attributed to the position of an object with respect to some reference system. And what else? Heat energy. Okay, this type of energy you get by burning things, all right? You may have heard of also energy associated with chemical energy. Okay, when you have chemical reactions, there's processes which occur where you have the transfer of this energy to undergo some reaction. Okay, so what we are concerned about, and you can look up all sorts of different forms of energy through the internet. We are primarily concerned with the balance of mechanical energy. Okay, so this is important for us, and this is, as I say, it's all there in the equations that we've developed in Newton's equations of motion. It's all there. It's just a case of having to try and tease this out. So what's the importance? Well, using energy balance or what we call energy methods is an important tool in solving mechanical problems, mechanical or dynamic problems. Okay, it can actually simplify what we need to do sometimes without doing brute force solutions to dynamic problems like we've been doing in the past. Mechanical energy is usually built in or inherent in these problems. Okay, that's the types of energy that you have in these problems. Some Mechanical types of mechanical energy are, of course, kinetic energy, because we have objects that move with a given speed in the problems we've considered, and also we have things like potential energy. Potential energy, due to the position of an object with respect to some reference system. And also you can go a bit further. You can associate potential energy as the energy input to a system by the action of some force. Okay, so right, input. Just another important fact. Surprisingly, when Newton developed his equations of motion, he didn't even use the notion of energy. So he didn't even mention this idea of energy balance, despite its importance. In solving dynamic problems today. Okay, so well, he just didn't need it, and that's fine, no problem. But it's just really interesting that it happens to be quite an important method used to solve problems. But anyway, he just didn't go through on this, and it's not a problem. Just he didn't feel he needed it, which is okay. Okay, so okay. Now what we'll do is we'll now have a look at this mechanical energy conservation principle. Okay. So we will meet from now on the following conservation law. Described by this equation. And you'll see that this crops up everywhere in the problems we've met. So we have the following. A quantity T plus a quantity V equals E. Okay. I'll just define what these terms are. So this is what's known as the kinetic energy. And we'll define this explicitly in a second. This is the potential energy a particle has. And E is what's called the total energy in the system. We consider. It is always constant. Okay, it's a number. All right. This thing can be a function of x, for instance. Okay, so the things on the left can be functions. This thing is a function of v, the speed, function of speed. And it depends also on the mass, but that's another story. Okay, so what's happening is on the left you have two functions which can change depending on the position and speed of the object. But when one changes, when one increases, it's at the expense of the other function, which should decrease in order to make sure that this thing here on the right, the sum of the two gives you a constant on the right. Okay, so let me just go through this. So first of all, kinetic energy. Okay, kinetic energy. Energy is energy a particle has due to its mass and speed at time t. Okay, so this has actually, I can state the form of this very easily. This has the form 1/2 times the mass. You may have already seen this, those of you who've done A-level physics, times the modulus of the velocity vector squared. Okay, velocity vector. So you take the absolute value of your velocity vector at a given time t. You square it, you multiply by m, you multiply by 1/2, and this gives you the kinetic energy. So this is what this is in star. All right. Okay, fantastic. So we know this. This is the definition of this. So here we can inspect the units of energy. Notice I've introduced this concept of energy, which is a quantity the objects have that give the objects a potential to actually carry out some form of action. So we can inspect this quantity to get the units. You're going to see this, by the way, coming up quite a bit when we start deriving energy balance principles from the dynamic equations we tackle. So understand the units of energy. So here we know that m as the units of mass. By the way, I'll just write this due to its mass m, and speed. By the way, I said speed. Speed we get in our problems from taking the modulus of the velocity vector. Okay, we know that the speed, that is as these units. So the speed squared is the following units. Okay. So this means that if I take this, well, this is equal to the dimensions of T, the kinetic energy, is the dimensions of M. Note that the constant 1/2 is dimensionless. So I just eliminate this. Multiplied by the dimensions of this gives us the following. Oh, by the way, I didn't put square there. Square. Okay. Right, which is, it's like a force, times a length. That's what it looks like. Okay, because the force has the units ml t minus 2, and then if you multiply this by something that has the unit of length, you get some energy quantity. Okay, so this is units of kinetic energy. Kinetic energy. Actually, it's the unit of energy. Notice that in star, we must also have dimensional consistency. Consistency, otherwise that equation is a load of crap. Therefore, again, therefore, V and E, and we can check this, also have dimension ml squared t minus 2. Okay, so, good. Next one is probably, you can't actually define this in a way that makes everything explicit like you can with the potential energy. So we'll just state this. Next one, potential energy in this formula. This is energy. An object has due to it receiving the action from some external force. Okay, you'll see this crop up in the equations F. Of course, you may have already seen this is the energy. This is also often described as the energy an object has. And you'll see this come into play when we look at how to calculate the energy given some F. Energy as described as the energy an object has due to its position. And this you'll see creep in the equations as well. Its position determined. Now you remember that we can determine using kinematics the position of an object by the position vector. Okay. And well, this is something we need to calculate. No real explicit formula just yet. I'm not going to complicate things by trying to say something about the potential energy more than this. You'll just see it come in the equations as it is. So E is the total energy in the system. And the most important thing about this is that this here is a constant. So this is the most important thing to take away. Now, how do we get hold of this constant? Well, you're going to see when we how this constant actually appears. And you're going to see how we actually determine this, okay? And then you'll see, then after this, you'll know how all this mechanical energy balance principle comes about. Okay, so this is what we've now got. So we're going to derive, or we're going to derive an energy principle for this case. So this is the derivation of the mechanical energy conservation law. When we have constant forces. Okay, so let's assume, and we know this, let's assume a particle of mass m is acted on by a constant force described by a vector. We won't model it, we'll just assume that we know it. Constant force described by vector f, 0. Then, what we know, Newton's equation of motion gives us the following. M dv, where this is the velocity of the object, is equal to f0. Okay, so that is what we would have. Okay, wonderful. So next thing, we know this, so let's do something different now. Let us now multiply both sides by the following. So we'll take the dot product of both sides with the velocity. Remember that this, by the way, this is a vector equation. It has 3 components. Associated with i's, j's and k's. I, j and k, the unit vectors. Remember this in general. So take dot product or scalar product. This we know how to do from linear algebra. Of this equation with the velocity vector. Okay, so then we get something like this. M v dot v dv, sorry, by dt equals f0 dot v. Okay. Now, a couple of things. Actually, I wrote star here. Let's change it to dagger. I'll bring it over to the other side as well. Okay. Now, a couple of things is, before we do anything else, we need to just recognize some terms on the left. So, before doing anything else, let's investigate terms in the left and right hand sides here. Okay, so first of all, left hand side. So we have this quantity, okay, which if I write out in the expanded form is Vx. I'm using this for the horizontal component of the velocity. Vy is the, x component of the velocity. Vy is the y component of the velocity, and Vz is the z component of the velocity. We've got the following. This is dot product with, now I'll just write this, I dvy by dt, j plus dvz by dk. Doesn't look like we can do anything with this, but look what happens. So let me just bring this on so it's not too squeezed. So on the left hand side, this clearly gives me vx dv by dt. I, it's a scalar product, plus vy dvy by dt, plus vz dvz by dt. Okay, now here we can actually do something about this. We can actually write this in another way. So you may recall using implicit differentiation, for this, see calculus. You may recall the following, that if I differentiate with respect to time the square of some function v, I have to first of all use the chain rule to differentiate what's inside, and then multiply this by the derivative of the outer function. So you may recall that this is dv by dt now, and multiplied by the derivative of the outer function gives me 2 v of t. Okay, so in other words, v multiplied by its derivative with respect to time is 1/2 the time derivative of the square of the function v. Okay, so let's go back to this. Let's use this. So we just replace on the right hand side of the equation smiley face, we just replace the product vx multiplied by its derivative of with respect to t by 1/2 d by dt of vx squared, and we'll do the same for the other terms so that we get the following. We get that v by dt is equal to the following: 1/2, using this rule, d by dt vx squared. Now, what about the next term? Well, it's of the same form, so it's just this. Now you might see what's about to go on, because we can still do some further simplification. You'll see that d by dt acts on the outside of these three functions. So I can write this as, and we have a common factor of 1/2, so I can write this as the following. Okay. And what do you know? You know what this is. This is associated with the modulus of v squared. Okay. So in other words, we have shown v dot v dv by dt is equal to 1/2 modulus of v squared. Useful to know, useful to use, in particular this formula here that I'm marking up in any direction of mathematics. Yeah. Okay, so that was the left-hand side. Now we go to the right-hand side. Now for the right-hand side. Now let's see if we can do anything about this. Well, we have this. Okay, so let me write this out. So let me do the following. So this is some force whose components are F1 plus F2J plus F3K. So this is expanded version of F0 in terms of IJs and Ks. And we assume we know what the components are. Good. On the other hand, well, what we've got is this. So is there anything we can do? Well, at the moment, we simply just have this, but what we should keep in mind is the following. That F0 dot V, according to this, if we do the scalar product, we have the following. F1Vx plus F2Vy plus F3Vz. Okay, I can go further. Remember that Vx, remember that this is, in fact, V is dr by dt, so I can say this is dx by dt, Vy is dy by dt, and Vz is dz by dt. And x, y, and z characterize the position of our particle in our reference system, whatever that may be. Okay, so this is in fact F1 dx by dt, and this is going to be useful in the next step. Can't really do much more with this at the moment, but really what we need is we need to know that this is what this guy should look like for the next step. Okay, good. So the important thing is we will use this next. Now, so this is really an aside note. Let me just block this off. So let's return to Dagger. So return to Dagger. And Dagger is this formula here. Okay. Dagger's this. So now we know that on the left hand side, this is now, left hand side is this 1/2 m d by dt of modulus of the speed square. And on the right hand side, what we have is this. Okay. So you might see where we're going with this in a second, because I want an energy principle. And you might be able to see already that left hand side is going to give us the kinetic energy. Okay, so this is what we go for. We're going to integrate with respect to t. Integrate now with respect to t. And what you have is this. So clearly m is constant, 1/2 is constant, so I have the integral of the left hand side, which is this. Okay, equals integral. I don't know why I just don't copy and paste this, save my poor hands from writing more. Okay, so we have this. Now, actually, we're experts at treating what goes on in the left, using a very famous rule. Okay, so clearly if I'm going to integrate, I'm going to get some arbitrary constant. This is going to go on the right-hand side. So this is, by the way, an indefinite integral. Indefinite integration. Now we're going to manipulate this on the left-hand side. So any constants is going to go on the right-hand side. They'll go on the right-hand side from now on. All right then. So on the left, clearly I have d by dt of some function integrated with respect to t. So this is nothing more than 1/2 mv squared, which is our t. Okay. This is equal to the following integral. Now I'm going to multiply out the brackets. Okay, almost there. Okay. Fantastic. Actually, you know what? I'm going to go further. I'm going to actually use the summation law for integrals. I'm going to put the integrals there. Okay. That is what the right-hand side is. Now, notice this. Well, common trick. We've used this so many times. I'm just going to write this down. This is this due to chain rule. Moreover, so we have this, and then these integrals to compute. Remember that F is a constant force. Okay, and because it's a constant force, this is real easy to compute. So these are constant, const. Okay, now, what else? Well, so we have this, f1 times x, f2 times y, when I integrate, f3 times z. And what else are we missing? Well, what we're missing is arbitrary constant of integration. Const of integration. Find using initial conditions, or find using some condition. Okay. Next, to find the potential energy is this. The potential energy of the system is defined as follows in this case. V equals minus F0 multiplied, dot product with R. That's precisely what we have on the right. This is in fact on the right here, F0, our vector, dot product with the position vector R. Okay, so this gives us, now remember that this is T, so this gives us, so we have the following. Now, you know what? Just for argument's sake, I'm going to call this arbitrary constant E, because that's what it is eventually, E, capital E. So we have the following. We have T equals minus V plus E. Okay. So rearranging gives us this. Now, notice this, by the way. This is a function, this V, I just wanted to make a point. This is a function, V of the position vector. So here, yes, exactly what I said before when we started. The potential energy is sometimes attributed to the position an object has with respect to some coordinate system, and this position is characterized by the position vector. So I have this. So rearranging just gives me exactly the law. Okay, so this is our energy, mechanical energy balance law. Okay, now again, what is the importance? Well, it tells us that objects will have some, if they move with some speed, will have some kinetic energy. V, if they have some position with respect to some coordinate system, they'll have some potential energy. But their sum of Ke and Pe, potential energy and kinetic energy, is always constant. Just move this on. It's always constant and equal to E, which is the total energy of the system. Total energy. And so if you stop moving, but you have some position with respect to a coordinate system, then of course your kinetic energy, T, will be 0, and the total energy will be equal to the potential energy you have due to the position. Okay? All right. So this is just an example of how one energy can grow with respect to the expense of another. Now, okay, let's. I wanted to just highlight something else. Now, the following concerns this, so I'm going to take this across. A very important thing that we actually completely glazed over when doing this is the following. So, in this development, we had the following integral. Okay, which is equal to this. Now, this is actually what we call the work done by the object. Work done by the external force. So this is what we call W. Here, W is the work done by the external force, F0. So forces do what we call work, external forces. How does a force do work? Well, a force does work by moving objects through distances. Okay, when we calculated this integral, you might say, well, that just is not apparent from this formula, because we have integral of f dot v with respect to t. Well, remember that when we worked this out, it was the following, f dot r. And where's the information about distance? So this has info about distance. Okay, your position vector tells you about the distance, and this is information about the force. Okay, so this is typically this was only in the case of 4 constant forces. Of course, if you don't have a constant force, what you need to do is, if the force is not constant, we would use the integral formula. Okay, this is the integral formula for work done. So it's the top one. Okay, and sometimes this is supplied with limits. So between T1, T equals T1 and T equals T2. So this is the work done by F. In the time interval. T1 to T2. Now, notice something. Notice F0 dot R has dimension, clearly. Force multiplied by length. Hence, dimension of work done is mL squared T minus 2. Okay. Also, dimension of, so this is only what we notice from the case of the constant force. So for constant force, and the dimension of the potential energy is therefore so we have to refer back to the formula for this, because this was F equals minus F dot R. Okay. Now, is it true when F's not a constant that these things have the same dimension? Yes, it is true. In fact, if F is not constant, work done and potential energy have same dimension. And there's an important thing here related to the following. Well, this actually shows us that if we have an integral, okay, with respect to some dimensional variable, then the result is equivalent to multiplying the dimensions of the result is equivalent to multiplying the dimensions of the integrand by the dimensions of the variable you're integrating with respect to. So just to highlight this point, we know that F dot V will have the dimensions of M L square T minus 3. You can calculate this. We know that T has the dimensions of time, T. Therefore, dimensions of work. The integral, effectively, when you integrate, you should multiply the dimensions of the integrand by the dimension of the variable you integrate with respect to. So you have this. Okay. So it's opposite of for what differentiation is doing. When you differentiate a physical quantity, you actually gain a dimension in the denominator of the expression instead here. So you divide by the dimension of the variable you differentiate with respect to. When you integrate, you multiply. So just keep this in mind. Okay, so what else do we need? One final example. So, object moving through gravity. I just wanted to highlight this. So let's go back to an easy case. Object moving through gravity. Moving under gravity. Moving through, moving under. Okay, so what we have is the following. So this is an example. So consider a stone, a thrown, dropped. Let's say dropped from some height. Then, of course, in previous examples, I've done the following. I've set up my reference system. Let this just be Z for argument's sake. Z representing our vertical height. It's positive direction pointing downwards. This is the stone. We know that the force that acts on this is Fg. And we know this is minus M. Sorry, that's wrong. We know this is a force with magnitude mg. I'm going to use, because in the past I used y as my variable, and correspondingly I'd use j. I'm going to use just k for this here, because now I'm using z. It has the sign plus because the force Fg, force due to gravity, points in the same direction as positive Z downwards. Force due to gravity is here. Okay, so let us do exactly the same calculation as before. So we know that Newton's equation of motion is this. M dv by dt equals mg. Okay, this is vz now. K, mgk. This is coming directly from the fact that we start with m dv by dt, the vector, equals fg. Okay, so this implies you have this, or, well, let's try this. No, in fact, let's not try that. Let's just go directly from this. So take the dot product of this equation. With v, which is vxi plus vyj plus vz. Okay. Then what you have is this. Of course, m. I'll borrow this. Okay. Now, clearly, the contribution from I and j in this left-hand side is not going to appear because our velocity only has a k component. So we have this. Then we have fg dot with the same. And then we have the same problem. It's not actually a problem, but we have the same thing going on. So we have something represented with ij's and k's, dotted with something that has a k component. So this is mgk. All right, so when I do this, what I get is m vz dvz by dt equals mg. Now, k dot with I, 0, k dot with j, 0, because that's the property of orthonormal basis vectors. K dot with k gives us 1. So we have this. Now, next I'm going to integrate with respect to t. And we'll get the following. So we are indefinitely. Don't forget, I like to normally do indefinite integrations. So we have this integral m v z dv by dvz by dt equals integral of mg with respect to t. Okay. Now, do you know what I'm missing? I'm missing a vz, clearly. Otherwise, this doesn't work. Okay, so I have vz dt. Then I integrate. When I integrate, clearly this is using our famous rule, 1/2 of m d by dt of vz squared. And this here is mg dz by dt. Okay, so we have this to compute. All right, so on the left I have integral of m over 2 d by dt vz squared. Don't forget dt now. Okay, dt equals integral of mg dz by dt dt. Of course, this is going to be dz. This is going to give us on the left, this whole thing here is 1/2 m vz squared. So this is the kinetic energy our object has traveling with the speed v downwards, vz downwards, okay, and this is now mg, just a second, may as well do the step, dz. All right, so we have this m/2 m vz squared equals mgz plus a constant, and this constant we'll call E. Should find using initial conditions. So this is our T. I can define this as minus V, i.e. so that my V is actually the following. So my V in this problem, so this is kinetic energy, and the potential energy is the following in this problem. V equals minus m g z. Okay. So, right. Okay. So knowing this equation star becomes T equals, now remember that V is this in my problem. So I have this, where the potential energy depends on E. Maybe it's good to point out that this T depends on Vz. So in this problem, I have the following energy balance law. Now, okay, so that is, if I write out the terms, 1/2 m Vz squared minus mgz equals E. So this is what we call potential energy due to the action of gravity. Or gravitational potential energy. Kinetic energy, usual thing. If you have some speed, then you and some mass, then you have 1/2 mv squared as your kinetic energy. So this is your conservation law. Okay. So in future, what we hope to be able to do is to drop the fact that we continually integrate to find that we have a half mv square as the kinetic energy, because I mean that's a fact of life coming from the dynamic term. What is the thing we need to calculate is the potential energy, because the forces are different for our circumstances. And we'll also need to investigate, when we look at some examples, how to calculate the total energy which comes from the initial conditions of the system. So we're all set up now to look at some examples. Thanks very much for your attention, and see you next time.